So this whole process that we're going to work through is called the rational root theorem. Um, the name of it, I know I've been trying to push us to focus on language. Yes, language is important here, but knowing that this is rational root theorem isn't all that important, but kind of thinking about what each step that we do along the way accomplishes for us is really important, right? So if we needed to find the roots, and remember that roots are solutions or zeros, they're all referring to the same thing, which are basically x values that make y equal to 0. If we wanted to find the solutions to this given polynomial, right now we don't have a method to do that. We can't factor that, okay? We don't have a method of factoring that. And so we need this whole process to try to pin down what are the solutions to this given polynomial. Okay, so can we factor? No. Can we guess? Yes, we could guess, right? If we wanted to find zeros or solutions, we could plug in blindly just some x values and hope that we get y to be 0. That's not very efficient though, especially when we're looking for a total of 5 solutions. Okay, so we need a process to kind of pin these things down. And that's where the rational root theorem comes into play. So in general, the rational root theorem, instead of us just blindly guessing x values that might make y 0, this helps us narrow down the guesses so that we can find a single solution. And once we have a single solution, we can then use division. It's going to be synthetic division that we'll use for this process to help us factor that polynomial until it gets to a form that we can work with it. Okay, so basically until it becomes a quadratic. So this part in bold here is how we come up with our guess list. Okay, that's kind of what we want to think about this as, is our guesses that we could come up with. Okay, so we're going to have 2 types of numbers that are guesses for solutions. Again, they're not solutions, just guesses. And those guesses, they're going to be whole numbers that the whole number guesses are factors of the constant term in a polynomial. Okay, so that's why, again, that language of knowing what the constant term is really important. So we'll focus on that piece here in just a second. So whole numbers are factors of the constant term. Then we're going to get some other guesses that are going to be fractions. And these fractions are in the form of p divided by q, where p, so the numerator, are factors of the constant term, so the same numbers that we identified earlier. And then q, which is the denominator, are factors of the leading coefficient. So for both of these types of guesses, we want to list out the factors of the leading coefficient and also the constant term. And so let's do that right now. Okay, so what are the factors of the constant term? Well, the constant term here is 5. Okay, so factors of 5 are 1 and 5. But know that in this case, when we're making our list here, these values can be positive and negative. So we will always say that our possible guesses are plus or minus whatever we come up with. Okay, so our guesses of what solutions might work are positive 1, negative 1, positive 5, and negative 5. And right now, we don't know if any of those work. It's possible that all 4 of them might work. Well, there's only 3 solutions. It's possible that none of them will work. Okay. Then we need to identify factors of the leading coefficient. The leading coefficient here is 2. So factors of 2, that's pretty straightforward, plus or minus 1, plus or minus 2. So now that we have these factors, we have to use what we kind of bolded in here to come up with the actual list. Okay, these numbers aren't the actual list yet. So remember that the whole numbers are just the factors of the constant term. So our whole numbers are plus or minus 1, plus minus 5. So these constant term factors are whole number guesses. But they are also the numerator. Okay, so they're the numerators for the fraction guesses, which makes the factors of the leading coefficient, those values of q in the p divided by q, these values can be the denominator for fraction guesses. Okay, but those factors of the leading coefficient are never going to be the whole number guesses. The only whole numbers are factors of that constant term. So now we need to come up with these fraction guesses. And so what I do is I take each factor of the constant term, knowing that they're my numerator, and I just ask myself what would happen if I take that number and divide it by a number of the leading coefficient. Well, 1 divided by 1, that's just 1, and I already have that on my list, so I'm not going to add that in. But taking this numerator of 1 and this denominator of 2 creates a fraction of 1/2. So plus or minus 1/2. Again, that 1 coming from fraction of the constant term, that 2 coming from the factor of the leading coefficient. So it's possible that 1/2 or negative 1/2 could be a solution here. I'm going to do the same thing with 5. Again, that can be the numerator. So 5 divided by 1, that's just 5. That's not a new number that I don't already have listed. So taking 5 and the denominator of 1 doesn't work. But a numerator of 5 and a denominator of 2 gives us a new number of 5/2. So plus or minus 5/2. So what we have here are 1, 2, 3, 4, and then factor in the plus or minus 8 different numbers that could be solutions. And that's our starting point in finding all the solutions here. Okay, so in a second, we will take these numbers and really we'll see if we can take those values and get them to be a 0 or a solution. And we're going to use that by going through synthetic division. So we'll come back to that in a second. I'm going to ask that you all try to come up with the same list for this second polynomial. Okay, so factors of the constant term, factors of the leading coefficient, and then the possible roots are whatever you come up with. Okay, so do your very best, talk with your group, try to come up with the same list, and then we'll take those numbers from our list and figure out which ones are zeros. Give you like 2 minutes to do that. Okay, so the list ends up being not too different from what we had in the previous polynomial. And that's because the constant term is 5 again. So we're going to get those same factors of 1 and 5 that are the whole numbers. And those values, again, can also be the numerators of any numbers or any possible solutions that are fractions. Okay, so plus minus 1, plus minus 5, and then 1 and 5 can be numerators. Does it ever make sense for 1 to be a denominator? No, right? Because dividing by 1 doesn't change the value that we already have. So when you're focusing on factors of the leading coefficient, the 1 doesn't really make a difference. I would only really list out the numbers that are not 1. Okay, so then how I got 1/3 was the numerator of 1, the denominator of 3. So 1/3. Numerator of 5, denominator of 3 is how I got the 5/3. Okay, so now that we have this list, that is an entry point for us to start to find all the solutions. So basically what this is telling us is with these polynomials, these are answers that could be, or these are numbers that could be zeros or solutions. Our next task is to figure out which of these are actual solutions. And we're really only looking for one. If we get one figured out, that's an entry point in us starting to factor this entire polynomial. Okay, so I'm actually going to skip the table portion. I don't know that we need to do that part because we're going to basically do it anyways. Okay, and let's just jump straight into the entire process together. All right, so we're going to almost start this from the beginning, okay, where our task is to find the roots, which again are solutions, zeros, x values that make y equal to 0. When we are asked to find all these solutions, really the first thing that we might try is to factor it. Okay, if it can factor, then this whole process we don't have to worry about. Okay, but this polynomial is not factorable. Okay, you could check that. It looks like it might be because we have those 4 terms, but if you group the first 2 terms and second 2 terms together, you're not going to find that you get a common factor after doing that. Okay, so we conclude that it's not factorable, so we're like, okay, we need another way to find these solutions, hence the rational root theorem. So we're like, okay, well, if I know I can't factor, I need to find one solution that works. And to figure out those solutions, we first need that same guessed not guessed, guest list that we generated previously. Okay, so this is the same equation that we had that I went through all together with you, where our guest list was plus or minus 1, plus or minus 5, plus or minus 1 half, and plus or minus 5 halves. So we're hoping that one of these solutions works. Now, there's lots of ways of how we could test these. We could just take an x value of 1 and plug it in and see what we get for y. We could plug in -1 for x and see what we get for y. While that's great, it's really tedious and it doesn't really help us with what happens next. We can actually do the same thing with synthetic division, and that's what we're going to jump to next. So after we make our list, our next task is to use synthetic division with one of these possible solutions until we get a remainder of 0. When we get a remainder of 0, now we're in business and we're starting to work towards finding all the solutions. Okay, so before I start to test numbers, how many solutions are we looking for? Or how many solutions will this polynomial have? 3. How do we know, Rylan? Good, the largest exponent, okay? Degree of 3 means that we are looking for 3 solutions. I cannot tell you how important it is to make that connection, because right away we know how far we need to go with this problem. Okay, so we're looking for 3 solutions, and again, that's because of the degree being 3. Okay, so we're going to test, and I just always start with the whole numbers. If I can avoid putting fractions in the synthetic division, I want to do that, right? Because it's just a little bit more complicated. We can definitely do it, but it's not as easy. So I just start with 1 and see what happens. So I'm going to put 1 in the chair. I bring down all the coefficients, so 2, -1, 2, and 5. And as we go through synthetic division here, we're really only looking for a remainder of 0. If it's not 0, it doesn't do much for us. Okay, so I'll bring down the 2. 2 times 1 is 2. -1 plus 2 is 1. 1 times 1 is 1. I get 3. 3 times 1 is 3. And I get a remainder of 8. So because of that remainder of 8, really what that means is that if I plug in 1 to this equation, we get a y value that's 8. Okay, that's another kind of unique thing about synthetic division, that it's another way for us to plug in x values and say what that simplifies to. So if I plug in 1 in this equation, we get the remainder, which is 8 in this case. Okay, so we don't like that. That doesn't do anything for us. And so we have ruled out that 1 is a solution. So now we're going to move on and just jump into the next possible solution, being -1. I'm going to use just a second. These sections are basically the same. I should have made it just one section there. So now -1, and we're doing the same thing. 2, -1, 2, and 5. Bring down the 2. 2 times -1 is -2. That's -3. That's 3. That's 5. And now -5 and the remainder of 0. And that's what we needed to have happen. We needed to get a remainder of 0. So we've done a couple different things here. Number 1, of our 3 solutions, we have confirmed that x equals -1 is one of those 3 solutions. Not only have we found the solution, but we have also worked towards factoring this polynomial. The result, or the quotient of this synthetic division, is 2x squared minus 3x plus 5. So what we just did is we took the original polynomial, 2x cubed minus x squared plus 2x plus 5. We know that it has a factor of 2x cubed, or that'd be squared, excuse me, 2x squared minus 3x plus 5. Again, that's a squared, not a cubed. And then times the factor that would give us a 0 of -1. So remember, by -1 being in the chair, that means we're checking to see if x equals -1 is a solution, and thus the factor is x plus 1. However, I get that right side to be 0. So the other factor here is x plus 1. So from this x plus 1, that's how we got this solution of negative 1. And our last two solutions come from this quadratic. We're going to get two more solutions here. And now that we're down to a quadratic form, we can use one of our quadratic methods. And this is a big reason why I had us do that quadratic remediation packet from first semester. All these concepts that we were supposed to work on first semester continue to show up. Factoring, quad formula, all those things are still present here. Okay, so to find these second solutions, I might ask, can I factor? So if this was factorable, I need to find two numbers that add to negative 3 and multiply to 10. I don't think those numbers exist. Actually, maybe they do. 5 and 2? 5 and negative 2? But are they going to multiply to... they don't work. Because they have to multiply to a positive 10. And if it was a negative 10, we'd be in business. So I don't think it works. Yeah. 2 times 5. Since a is not 1, we got to figure out numbers that multiply to a times c. So this doesn't factor, which means our last two solutions come from the quadratic formula. Okay, so we're going to use quadratic formula with the result from this division. So we're going to go quad formula. And that's x equals negative b, so that's positive 3, plus or minus the square root of b squared, so negative 3 squared, minus 4 times 2 times 5, all over 2 times 2. And we've got some simplifying to do. So this is 3 plus or minus. This would be 9. And then minus 4 times 2 times 5, which is 40. So 9 minus 40 divided by 4, which is plus or minus root negative 31 divided by 4. And I'm still going to ask that we do our best to simplify these answers that are in or that we get from the quadratic formula. So with this square root, we want to factor out perfect squares. Luckily for us in this case, 31 is prime, meaning there aren't any numbers that divide 31 besides 1 and 31 itself. So the only thing we need to do to simplify this is to take out the negative and make this an imaginary solution. These are the last two solutions that we were looking for. The positive, so adding the 3 and I root 31 is one solution, and the minus is the second solution. So from these, we have three solutions of x equals negative 1, another one of 3 plus I root 31 divided by 4, and then the other one of 3 minus I root 31 divided by 4. So three solutions, and we have all three of them. Remember that every solution has a multiplicity. All these solutions only show up one time. So we're going to say that it has a multiplicity of just 1. They do not show up more than the one time. The last thing I want us to make a connection to, when we get these answers that are real numbers, okay, so whether it's a whole number, a fraction, a square root, as long as it doesn't have the I in there, that value is an x-intercept. These other values are not x-intercepts because they are imaginary. Okay, they're still solutions or they're still zeros, but they are not x-intercepts. Our x-intercepts have to be real numbers. Okay, so this process, it takes practice. Okay, there's lots of steps here. More steps than probably any problem that we've worked with. Okay, especially each step is going to be a little bit different. So let's go through another one together, and I'm going to actually this is where we'll go back and forth and have you do some parts in your groups as well. All right, possible roots. This is the same list we did before, so let's just add in what we already had. So plus minus 1, plus minus 5, plus minus 1/3, plus minus 5/3. And this is where I'm going to have you try something. And I think it'll be best if we kind of do one piece at a time. And then we'll talk about where we're at and then figure out how to go from there. Okay, so just like I said at the start of class, please try these things when I'm asking you to do so. Okay, I'm just going to ask you to try some synthetic division with certain numbers. All you got to do is try your best with it. But if you sit there and do nothing, it doesn't help you at all. So let's first see if 1 is a solution. So I won't throw 1 in the chair, carry out the synthetic division, see what you get. If you do not get 0, you can move on and plug in -1. Okay, I'm going to start with 1 and just see what I get, and then we'll chat together and see what's going to come next. And at this point, with the synthetic division, that's really all we care about. Are we going to get 0 or not 0? Okay, the actual remainder that we get, yes, what that's telling us is that if I were to plug in 1, so x equals 1 in every x in that equation, we would get a y value of -32. Okay, so yes, if we wanted to graph and get points, that might be beneficial here. We're not focusing on the graph. We're just trying to get the solutions here. So by us not getting 0, that just means that 1 is not a solution. And so we would move on and try -1. So same idea, 3, -10, -24, -6, and 5. I want everyone to try -1 if you have not done so already. I'll give you a couple minutes to do that as well. Again, all you're looking for is a 0 or not 0. If you do get 0 here, pause for a second. So we're going to go a little different direction after getting one solution here. All right, did we get 0 here? I got 0. That's a good thing. Okay, when we get 0, now we're making progress towards finding these solutions. So again, let's talk about what we have done up to this point. We have figured out that -1 is a solution, and thus x plus 1 is a factor. Okay, I do want us making that connection. So down at the bottom, it says state all solutions, and we know that we're looking for 4 solutions. And we know that x equals -1 is one of those 4. Okay, so as soon as we get a remainder of 0, we have made some progress towards finding the 4 solutions. Now, we want to, again, think about what this equation is, because this equation is where we're going to get our remaining 3 solutions from. So remember that 0 is our remainder, 5 is the constant, -11 is linear, -13 is quadratic, 3 is cubic. So our remaining polynomial is 3x cubed minus 13x squared minus 11x plus 5. And now we're trying to figure out where does that equal 0. Okay, so we factored out from our original polynomial an x plus 1. So if we wanted to write this in its factored form, we would say this cubic function times x plus 1 equals the original equation. We don't need to do that. But we do need to make the connection that this is what we're currently working with. This is our remaining factor. And our last 3 solutions come from this. So again, it's almost like we start over and we ask ourselves, okay, is this factorable? If we can factor, that saves us a lot of time. Okay, so to check to see if it's factorable, I notice there are 4 terms. I'm like, okay, if I take out GCFs of these first 2 terms and second 2 terms, am I going to get that common factor? And the answer is no, right? 11 and 5 are prime. There's no GCF there. So this is not factorable, which means we basically start this whole process over again. We need to check more numbers using synthetic division until we get one that works again. Now, here's what's nice. I don't need to make this list again. We can just continue to use numbers from that list. But what tends to happen is we forget about multiplicity. and that solutions can show up more than one time. And so usually what I would suggest is if you get an answer that works like -1, just try that again and see if it works again. But this time we're using these coefficients as opposed to the original ones from our quartic polynomial. So I'm going to use -1 again, just in case that solution shows up twice. And for my synthetic division, I'm going to bring the coefficients from that cubic polynomial. So bring down the 3, -3, -16, 16, 5, -5, and 0. And that's kind of sneaky, right? If we don't think about multiplicity and the fact that an answer can show up more than one time, a lot of you probably would have checked 5. And 5 might work, I don't know. Or maybe you check -5, that might work, I don't know. And then last resort, we're having to check the fractions. Okay, but again, I always kind of avoid working with the fractions unless I'm forced to. And the only way I'd be forced to is if all those whole numbers did not work. So again, what have we done so far? We have found another solution of -1, and instead of listing it twice, we can state that it has a multiplicity of 2, and thus it counts as an answer twice. So of our 4 solutions, we have found 2. -1, 2 different times. The remaining polynomial is 3x squared minus 16x plus 5. And we need to figure out where does that equal 0. And in your groups, I'm going to have you all figure this out and find our last 2 solutions from there. And I actually want some. So when I get down to this quadratic, again, I prefer to factor. If it factors, I'm going to factor it. The way that I check that is if I can find 2 numbers that add to b, so add to -16, and multiply to a times c, which is 15. In this case, those numbers exist. Those numbers are -15 and -1. Now, did you need the factor? No. You could always get to the a quadratic and then just use the quad formula. Okay, at this point, I don't really care how you solve the quadratic. To me, factoring is just a little more simple. So these 2 numbers, they take that middle term and they split it up. So minus 15x minus x plus 5 equals 0. Then I'm going to group the first 2 terms and the last 2, where the GCF is 3x, then times x minus 5. This is -x plus 5, so those signs are opposite what they need to be. So I'm going to factor out a -1. X minus 5 is that common factor I was looking for. And I get 3x minus 1 equals 0. After we factor, I take each factored term, set it equal to 0, and solve. Where I get x equals 5. And 3x equals 1, giving me x equals 1/3. So our last 2 solutions are x equals 1/3. That has a multiplicity of just 1. It only shows up one time. And x equals 5, which also has a multiplicity of 1. Last thing, and then we can start to pack up. Block day will be a work day for this. Because all of our answers were rational, meaning all of our answers could have been written as fractions, you could have used that synthetic division the whole way through, right? 1/3 showed up in our original guess list. 5 showed up in our original guess list. So if you were to plug in 5 or 1/3 into synthetic division, it would have also given you a remainder of 0. All right, we got to a really good spot today. That's going to allow us to basically have a work day on block day. We will do some warm-up stuff together, but most of that period will be your time to work on this process.